So this pack is called linear transformations. The definition of a linear transformation, obviously, it's a transformation that it's something that transforms points, basically. So moves points onto other things. But importantly, for a linear transformation, the origin is not moved by the transformation. So translations don't count as linear transformations because they would move the origin. Okay, but rotations about the origin don't move the origin, they're fine. Enlivenments out from the origin are fine. Reflection lines that go through the origin are fine as well. All of these are linear transformations. A linear transformation takes a point and maps it onto what's called the image. Okay, and linear transformations can be represented by ax plus by and cx plus dy. There, basically, combinations of x and y's and stuff. Notice that there's no squares or anything in there, hence the linear, it's just x and y's. And there's no like +1 or there's no like numbers on their own without an x and y in there, because again, that wouldn't be a linear transformation. And you can represent this by a matrix, just like how you could write simultaneous equations in a matrix. You can write this ax plus by in terms of a matrix. Okay. So sometimes you'll see this notation. It's kind of like mapping notation for a transformation, but most of the time we just use matrices. So we've got 3 transformations here, and it wants us to find the image of the point 2, 3 and work out whether it's a linear transformation or not. So for this first transformation S, we're taking the point 2, 3. And we're mapping that onto its image. So I'm substituting in x is 2 and y is 3, which maps it onto the point 6, 2. And then the question is this linear or not? This one is not linear because it's not the form ax plus by, cx plus dy, because it's got this +4 and this -1 here. So this is not a linear transformation. For the second one, mapping 2, 3 onto a new point. So I do 2 times 2 minus 3, and I've got 2 plus 3. That once that maps it onto 1, 5. This one is a linear transformation because it is in that form ax plus by and cx plus dy. So this is fine. This is a linear transformation. And for this final one here, this one maps 2, 3 onto 2 times 3 and then -2 squared. Maps it onto 6 minus 4. This one isn't a linear transformation because it's got a squared down here, so it's not linear. So reasons for these, the first one, if you think about what would happen to the origin for this first one, if you substituted in 0, 0, you'd get the point 4 minus 1. This one moves the origins. This one's like combination of translations. So this one's not a linear transformation. It would move the origin. This last one, if you subbed in 0, 0, it's fine. You would get 0, 0. So this one doesn't move the origin, but it still doesn't mean it's a linear transformation. So this one's not a linear transformation because it has x squared in it. Example 2 here. So it asks us to represent these linear transformations as matrices. I'm just going to rewrite this with the x first and then the y. And this 3x, you can imagine there's 0 y on that. So to represent this as a matrix, call it the matrix T. This is 1, 2, 3, 0. I'll do U as well. But for U, there's no X on the top one, so that's 0 minus 2. And then on the bottom one, it's 3. Okay, so if you're given the matrix transformation in terms of a matrix, to work out the image of a point, what you do is you take that matrix and you multiply it by the point, but you write it in a column vector instead. To do that matrix times 1, 3. So I've got minus 2 times 1 plus 1 times 3. Gives me 1. So that's first row times first column. And then second row times the second column. So I do 7 times 1 plus 2 times 3. That gives me 13. This is the image of the point 1, 3. Thanks for your time. Okay, thanks. So this one, so do the top row times the first column. So you get minus 2 times minus 2 gives you 4, plus 1 times 5 gives you 9. And then you do 7 times minus 2 gives you minus 14, plus 2 times 5 gives you minus 4 for that image. This next one has us going backwards. So this next one has gives us 2 points in their images and asks us to find the matrix M. Probably the best way of doing this is just to write the matrix M as generic matrix A, B, C, D, and we're going to work out what A, B, C, D are from that. So first off, if I do M times 2, 1, I know I get 1, 3. And so if I do this multiplication, I get 2A plus B equals 1, and I get 2C plus D equals 3. I only need 1 equals sign there, really. Okay, so I've got 2 equations there. I can do the same for the other point. So if I do A, B, C, D, times 1, 1, get 3, 1, which gives me 2 equations. I get A plus B equals 3, and I get C plus D equals 1. Solve these pairs of simultaneous equations to work out your A, B, and C. So I've got these ones involving A and B. You could type them in T-calculator, or you can solve them by hand quite easily. So if you subtracted these, you would get that A is minus 2, which you get rid of the B. If you substitute in A is minus 2 into this, you'll get minus 2 plus B equals 3, so B is 5. And then you can do the same for the other ones. So C plus D equals 3. And C plus D, 2C plus D equals 3, and that C plus D equals 1. Again, you can subtract those. You get rid of D, so you get C equals 2. And then if you sub C equals 2 in, you can get D equals minus 1. So your matrix M is equal to minus 2, 5, 2, minus 1. Have we got the one underneath? And I'll pop the answer up in a few minutes. Right, this last example I'm going to do is similar to what I'm going to do in the next few lessons when we start looking at rotations and reflections and things like that. So we're going to be looking at what's called the unit square. So this is a square with side length 1, which we can say has vertices 0, 0, 1, 0. So this is A, 1, 1. I'm going to say this one's B, and 0, 1. So this one is C. So here's your unit square. It wants you to find the vertices of the image of S under this transformation here. Now, what you can do, obviously, is you can do this matrix times by each of these points individually and work out their image individually. Or you can do them all as one big matrix and do it all together. So I'll do it that way, but either is fine. But the way to do it all together as one big matrix is to do the matrix, the transformation matrix, the minus 1, 0, 0, 1, times by a matrix that has each of these in a column. So I've got 0, 0 in the first column, 1, 0 in the second column, 1, 1 in the third column, and 0, 1 in the fourth. Okay. Saves you having to write out that transformation matrix 4 times. Do this matrix multiplication. So I'm doing minus 1, 0 times 0, 0. Obviously, gives you 0, 0. So I'll just give you 0, 0, 0. Minus 1, 0 times the second column, so that's minus 1 times 1 plus 0. Third column, minus 1, 0 times 1, 1 gives you minus 1. And the final one, so minus 1, 0 plus 0, 1. 0 times 1 gives you another 0. Got the first one. Go on to the second row, multiply by all these columns. So 0, 1 times 0, 0, 0, 0. 0, sorry. 0, 1 times 1, 0. So 0 times 1 plus 1 times 0 is another 0. 0 times 1 plus 1 times 1 gives you 1 for the third column. And 0 times 0 plus 1 times 1 gives you another 1 for the fourth column. So these are the vertices of the image of S. So we've got 0, 0, we've got minus 1, 0, we've got minus 1, 1, 0. It asks us to sketch S, which I've already done, and it's image S dash on coordinate grid. So you see that little dash, that represents the image of a shape. So plotting these points, so we've got 0, 0, we've got minus 1, 0. So this is the image of A, so I'll put A dash. I've got minus 1, 1, so this is the image of B, so I'll put B dash. And I've got 0, 1 for C. So C and C dash are actually in the same place. So this is my square S dash over here. This one's S.
John.
Yes, Jeff.
When did you get into my ball painters?
So this one, this is made up of all of the points in S. So this is the origin, this is the point A, this is the point B, and this is the point C, each of these columns. You can do them one at a time, or you can do it all together like that. In doing this, you can see what transformation has happened to S to end up with S dash. So you origin and C have stayed in the same place, but A and B have been flipped over there. So this has been reflected in the y-axis. Okay. I'd like to have a go at that question for you underneath. So do a very similar thing with that one. Answer to this one, so they've done them individually. So each of the images are there. If you draw it, well, it's a couple of rectangles. So there's one down here and one down here. The single transformation that's happened to this is it's been rotated 180 degrees about the origin. You don't have to say which direction it's in because it's the same both ways. But like Dan says, you can reflect in the y-axis and reflect in the x-axis, and you will get the same